Okay, this problem asks you to draw the resonance structures and the resonance hybrid for both nitrate and sulfate. Now, a resonance structure is when you have two equivalent Lewis structures that differ only by the application of a double bond, where that double bond is located. Now, you might get to, when you have a formal charge test situation, you could also say that that's resonance. But in general chemistry, we're really going to limit our resonance vocabulary to situations where the only difference in the Lewis structure is the position of the double bond, and you've decided it's the best Lewis structure. So with nitrate, we would do everything else the same way that we would with drawing Lewis structures. We get 24 electrons. We'd end up with something that looked like this. But we would realize that we could have moved that double bond in a variety of different locations. It could have been down. It could have been off to the left. And so these three structures are the resonance structures. So I've drawn all three of them. How do I draw a resonance hybrid? The resonance hybrid is a mesh, is a single picture that represents all the different resonance structures. So what's the same in every single resonance structure? Well, in every resonance structure, there's at least a single bond to an oxygen. In every resonance structure, there's at least two lone pairs on each oxygen. Well, where are the missing electrons? Well, not only are they spending some of their time around the oxygens, they're also spending some of their time bonding the nitrogen and oxygen together. So if you were to, this is an illustration of the limitation of Lewis structures. If you look at individual resonance structure, you might say double bonds shorter than single bonds. So nitrate has two long bonds and one short bond. But the resonance hybrid really tells the actual story. It's a better depiction of the actual molecule than Lewis structures can provide. We would say that the nitrate molecule, it doesn't have single bonds, it doesn't have double bonds, but has something in between. And whatever it is, we know that all of the bonds are the same. And so we would say that nitrate probably has three identical bonds to oxygen. And so again, these are the three resonance structures, and this is the resonance hybrid. Now, for sulfate, you get into the same situation. Here's that resonance hybrid. For sulfate, you would have to go through the Lewis structure, but you would have done the formal charge test. And the formal charge test would tell you that sulfur is better with an expanded octet for this molecule. And so that's one of the possible structures you could get. And so again, we were just going to think about where are the possible locations for the double bonds. Well, it could have been both of them up and one of them to the left. Could have been one of them up and one of them to the right. And the other possibility is that they could have both been down. And so I'm just going to fill out the rest of these Lewis structures to show you the different resonance structures. Remember, all of these differ only by the positioning of a double bond. Okay, and so I'm still going to add my brackets. I add these double-headed arrows. Double-headed arrows mean resonance. And I'm going to go back. I'll have to eventually add something to one of those structures. But let's draw the resonance hybrid. So what's the same in all the structures? Well, at least one bond to each oxygen. Also, at least 1, 2 lone pairs on each oxygen. Where are the rest of the electrons? The rest of the electrons are not only around oxygen, but they're making bonds between sulfur and oxygen. So we get the same sort of conclusion here. I've got 4 individual resonance structures. Let me draw the 2 minus there. And I've got 1 resonance hybrid. The resonance structures are Lewis structures. The resonance hybrid is a different type of picture. The resonance hybrid is closer to the real molecule than the Lewis structures, but it doesn't follow the rules of drawing Lewis structures. Okay, that's that one.